Welcome to the 27th ICANX lectures in our third series in the ACS Nano Rising Star lectures. Paul Weiss at UCLA, coming to you early in the morning from Los Angeles. I'm joined today with my co-host and fellow editor at ACS Nano, Andrew Wee, as well as Alice Zhang, who organizes these lectures, and my student, Mr. Chuanzhen Zhao, soon to be Dr. Chuanzhen Zhao, who helps us along. We're delighted to have a fantastic lineup for you today. We have 3 lectures, also supplemented by a panel in between. We have Professor Youfan Hu from BEDA, Professor Goki Eda from National University of Singapore, who will be introduced by his colleague, Professor Wee. And then we have Professor Maria Lakutskaya from ETH. So in these lectures, we showcase rising stars from around the world. You'll also see later a write-up of how they think about where their field is going in a perspective in ACS Nano. And this is our attempt to connect everyone around the world with these people we'd normally be seeing at conferences and showcasing their work. And so we wanted to share their extraordinary accomplishments and thoughts with you today. So thank you for joining us wherever you are in the world. And let me move ahead then. As I said, these are the Rising Star lectures. And I'll point out that these 3 scientists will also serve as advisors to ACS Nano starting today. Our first speaker is Professor Youfan Hu from BEDA. She got her PhD also at BEDA in physical electronics. She's now an assistant professor in the Department of Electronic Engineering and Computer Science. After her PhD, she went to Georgia Tech, where she was a postdoc and also a research scientist. She studies energy harvesting, carbon nanotube devices, and nanosensors. She's an associate editor of IEEE Transactions on Nanotechnology, actually a sister journal to the one where I got my start. And we're delighted to introduce her, and her talk today will be on carbon nanotube-based high-performance flexible electronics and integrated smart sensor systems. Professor Hu, the floor is yours.
Okay, thanks, Paul, for the introduction. And also it's my great pleasure to be on this stage. And I would like to share with you some of the recent progress we have done related to the carbon nanotube-based flexible electronics and integrated smart sensor systems. First, let's take a look at this picture. At the development of the technology, the forms of electronics devices has also been changed from the immobile one to the mobile one, and now the wearable ones. During this process, the sensor technology plays a key role here. And there's several visionary organizations have created this trillion sensor forecast. But it should be mentioned here that the sensor mentioned here is referred to smart sensor. So what does the smart means? First, let's take a look at the typical commercial sensor available in the market right now. Here shows our geomagnetic sensor, which is used for the digital compass. And first of all, we see that the size of the sensor is very small. So we see has been the miniaturized for better integration capability. Second, if we checking the block diagram of the system, we see that here's the sensor part, and all of the rest is for the signal processing. So for the sensor, which has this built-in signal processing capability, we called it as the smart sensor. And we see that the power consumption of such a sensor is very low. This is because And as more and more the application of the sensor was in the variable or mobile or the remote forms. So in such a condition, the power supply is very restricted. And as we all know, that one great application of the variable smart sensor system is for the healthcare monitoring or the medical monitoring. To interface the skin or the soft tissue, we need such a system to be flexible. Here, just to show two very great examples of the current research status of such kind of flexible integrated smart sensor systems. And it demonstrated that they can be used for in vitro or in vivo monitoring. We see that here it has a flexible sensor arrays and or maybe the flexible probes, but the signal processing unit in such a system is still relies on commercial hard silicon chips. In such a hybrid system, there will be some kind of the localized strain between the flexible and the rigid parts. So there may be some stability issues when the system was on the deformation. And also we see here that the hot spots may be generated just below the chips. So when you integrate it or interface such a system with the biological tissue, there will be maybe some challenges. We have to say that when we're talking about the flexible electronics, we always emphasize that they have some advantages over the traditional one, including they can providing conformal contact with the biological tissue. They have excellent biocompatibility, but also there's a issue here. At the core unit of the system, the flexible integrated circuits with high performance and low power consumption, also at least medium scale integration scale for the built-in signal processing and analysis capability in a timely manner for such kind of flexible integrated circuits is still late if we want to get the fully flexible systems. So for in my group, our research interest is about the flexible integrated smart sensor system for healthy and medical monitoring. In such a system, we have the sensors, the flexible sensors, to capture the information from the human body. And also, we build such kind of flexible ICs based on carbon nanotubes to realize the function for their in situ signal information processing capability. To start talking about what we have done, I think there is a first question we should answer. The question is why we think that carbon nanotube can do the job. Carbon nanotubes have a lot of fantastic properties. There just to show several examples. First, it has an ultrathin body, so that means it can get a very good electrostatic control of the channel. So it has a very good properties when you scaling down the device. And also, it has the symmetric band structure, so you can get matched properties both in the electrons and holes. It will make the design of your transistor much simpler. And also it has a high mobility. So for the devices, that means you can achieve much higher speed in your device, or we see the high performance. And most importantly, for the flexible devices, because there is a lot of restriction for the fabrication, either polymer or we see the flexible substrate cannot resist high temperature. So for the carbon nanotube, they have very special properties. That is the polarity of the device, of the transistor, can be controlled by the contact metal. So that means you can using a low processing temperature to realize both P-type and N-type transistors for the CMOS technology. And also, the carbon nanotube can be solution processable. That means you can get a mass production on a large substrate, and it has a very great mechanical properties. It is very great for the flexible devices, and also it is transparent. And until now, there has been a lot of demonstrations of the flexible ICs based on carbon nanotube thin films. And they have showed great potential in this technology. But if we compare the one we achieved in the flexible substrate to their counterpart on the rigid substrate, there's still a big gap here, including the performance, including the power consumption, integration capability, and also the functionality. So what we try to do is that we try to just extend all the advantages the carbon nanotube has achieved on the rigid substrate, and just extend this advantages into our flexible form. First, I will introducing the system we have realized about the ultra-thin electronic foils with CMOS flexible ICs. As we all know, for a system and its bending stiffness, its conformability, and also its adhesiveness to the soft tissues is proportional depending to its thickness cubed. So that means if you can just reduce the thickness of the system, then you can realize some kind of the ultra thin system. You can get the ultra flexibility, and most importantly, you can get a perfect or better interface between your electronic devices and the soft tissues. But we also say that when you greatly reduce the thickness of the system, the manufacturing will be more challenging. So how can we realize to achieve the ultra flexibility simultaneously with the high performance? Here's our strategy. Here showed that we started with the silicon wafer, and then we grow some kind of the ultra thin substrate on the silicon wafer. And then we finish the fabrication of our CMOS device on the ultra thin substrate. Then we get the system delaminated from the silicon wafer. So when we did the fabrication in this step, how we can achieve high performance during the fabrication, we did a lot of things. The first thing I've mentioned is that because in the carbon nanotubes, the polarity is dominated by the contact. So that means this makes us can just directly fabricate their CMOS on the ultra-thin substrate. And in this system, we're using the palladium as the electrode for the P-type transistors, and we use the scanning to realize the N-type transistor by injection of different kind of carriers into the channel. And during this fabrication process, the hover temperature, the highest temperature can be well controlled below 150 degrees. And the hover system, the thickness of the hover system can be controlled around several micrometers. And another thing we did is that we using the PVP to planarization of the surface of the S-ground ultra-thin substrates. We say that before the planarization, the roughness of the substrate is very high, around 5 nanometers. After the planarization, the mean roughness can be reduced to be below 1 nanometer. And such roughness have a very great effect on the obtained device's performance. And thirdly, we using another layer to just package our device to make all the active device was in the neutral mechanical plane of the system. So the obtained device or the system can have a better mechanical deformation capability. And after the fabrication of device, now the second thing or the second issue is how you can just delaminate all the system from the fabrication substrate without any performance degradation. And there are a lot of choice of this process. You can use a lot of technology. One of the example is that generally you can using a thermal-released tape to transfer the whole system from the substrate. But there are a lot of limitation about this technology. It is limited by the handleable dimension of the system, and also the device yield will be a problem, and also the performance of the device. So during this process, we developed a new technology, which is called capillary-assisted electrochemical delamination. In this process, we see that here, the electrochemical reaction was happened just on the silicon surface. Here is the silicon substrate on the silicon surface, and it is happened, the reaction is just happening in a very narrow gap, which is just between your polymer substrate and the surface of the silicon substrate. So for this process, the setup is very simple, and the delamination process is very, I think it's very quick, because for a 2-inch wafer, it only takes 40 to 50 seconds. It's very quick. And as all the reaction was happened below the substrate, so there is no chemical contamination to the device, to your device on the surface of your polymer substrate. And also because this gap is very small, which is generated due to the capillary effect. So there's no mechanical damage of your device. And at this method has nothing to do with the property of your polymer substrate. So it can work with almost of the general polymer substrate. We tried it on the PI film, and also the PMMA, and also the SEBS film. They can all work very well. And here for the PMMA, it is only 200 nanometers. And so you can see this system is very robust. And then after all the efforts, we need to check what's the performance of the device we get on such a ultra-thin substrate. And here show the transistor, the P-type and N-type transistor we get on the finally substrate. The number here just deliver one very important information is that the device performance we get here on the flexible substrate is at the same level, or it is similar to the one the counterpart achieved in the rigid substrate. So that means in this case, we can achieve ultraflexibility simultaneously with high performance. So that's very important. So we see that there's no barrier between the flexibility and the performance. And because the whole system is very thin, just 4 micrometers, so it has ultraflexibility. You can bending your system, and there's no performance degradation after such a mechanical deformation. And also, we constructed some kind of basic logic gates. Here show the CMOS inverters, and we check the power consumption of these logic gates. You can see here the power consumption, the active power here you used for realize one 0 to 1 switch is only is less than 0.25 nanowatts. It's a very low active power. And then we did the speed evaluation. We constructed the 3-stage CMOS ring oscillators, and it showed that in our device, the single gate delay is only 33 nanoseconds. It's fast. And finally, we integrated the ring oscillators with the humidity sensor, and we can put the whole system attached to the skin. And when your skin is dry or get sweaty, then we find that the oscillation frequency of the ring oscillator can be switched. And so by this method, we can just convert an analog signal into a frequency information. So at this stages, the information can be ready for wireless transmission. And in such a system, the power consumption for the humidity monitor system, the power consumption in the active state is around 50 microwatts, and in the standby stages is only about 1 microwatts. This is the first thing we have done. The second thing that here showed there, we did something about the transferable system that can work with biologic surface. And in this case, we're using a method called transfer fabrication. So by using this method, we can just separate the fabrication process from the destination substrate. So that means you just get the limitation about the fabrication on the polymer substrate, get rid of the limitation. So in this case, by introducing or using our sacrificial layer during the fabrication, then we can, through our dry etching or wet etching process, to make the transfer, to transfer the whole system to at the end of the fabrication to the destination or the target substrate. And this fabrication can be done on 2-inch wafer, silicon wafer. And in this during this transfer process, we checked the device before and after transfer. And here's 2 curves show that they are almost the same. So that means the transfer process itself put very minimal effect on the device performance. And if we further check the number, these numbers here, the threshold voltage, on-off ratio, off-state current, we can get some more conclusions. Here, our device showed a arch low off-state current, which is 0.1 picoamp per micrometer, and it also get nearly ideal SS value, and also it has a very large on-off ratio. All these numbers means that we have realized the ultra low power consumption in these transferable devices. And to realize these properties, we did something. The things we did is that we're using HMDS passivated the interface between the silicon, between this the polymer substrate and the carbon nanotube thin films. And also we realized the growth of high K dielectric at a very thin thickness, about 20 nanometers on the flexible or the substrate, flexible substrate. So both of them contribute to the realized ultra low power consumption in these devices. And we also constructed some the basic logic gates, and in this case, the minimal static power consumption realized here is only 0.25 picowatts in the inverters. And we can construct more complicated circuits. Here shows a full adder, and most importantly, the whole system has very great biointegration capability. we can transfer the device to the surface of the leaf or contact the lens or just our body surface. And this biointegration capabilities not only just transfer the device on the biological surface, but also the device can work on the biological surface. And here show that our device can be operated on a curved planned leaf. When you bending the leaf and both the transistor and also the logical gates can work correctly. So there's no performance degradation when they are experience the mechanical deformation on the leaf surface. And this is the second work we did. And next, I will introduce some interesting thing about the degradable ICs for eco-friendly sensor nodes. And as I mentioned in the last part, I will say that this transfer fabrication process can make the whole system compatible almost to any kinds of the target substrate. So when you transfer the whole system to a degradable substrate, and also you using the degradable materials to construct your device, then the whole system can be a degradable this integrated systems. And here we show that by using the transfer fabrication process and also combined with the delamination method we mentioned before, the capillary effect assisted electrochemical reaction, then we can realizing our degradable ICs with high yield and high uniformity. Here show that we can fabricate these degradable transistors or ICs on a 4-inch wafer. And then first, it can realize a 100% transfer rate. And then we test all the device transferred from the wafer, and we take 10 chips from a different location, and all the device have an average device yield about 96.6%. And we see that this green region, for this region, all the chips have a 100% device yield. And also, they have a very great uniformity. Here show the result. We just calculated the device from every chip and among different chips. So we see that there's very small fluctuation on the same chip and also between different chips. So that means the uniformity is very good, not only on one chip, but also among different chips. And for this kind of device, we can integrate it with some kinds of degradable sensor to construct this kind of sensor nodes for environment monitoring. In this case, we integrated our sensors with the UV sensor, which is constructed based on zinc oxide thin films, and also the temperature sensor, which is constructed with the PEDOT-PSS. And because all the material used here, the metal we used here is aluminum, and the dielectrics we used here is aluminum oxide. So all this, the material used here are degradable. So in this case, we attach the sensor node on the plant surface, and then we carry out a real-time monitoring outdoors. We recording the change of the temperature and also the UV light sensitivity, the intensity. And here is the result compared to the data recorded by the commercial temperature sensor and the light power sensors, and they show the similar changing trend. So that means it realized some kind of a very fidelity monitor about the environment. And as I mentioned, all the construction material used here are degradable. So we did a demonstration that we just introducing artificial rain to monitoring the raining conditions, and then after 90 minutes, and the sensor nodes was just degraded in the environment. So it can be used at the eco-friendly sensor nodes and for the distributed environment monitoring. Here's the third demonstration, and for the last one, it is configurable ICs with multiple functions. In this case, this part is some different from the three things we just introduced before. There's a huge demand for such kind of configurable electronics. They can be used in medical applications or maybe in some of the defense applications. There's a lot of technology used for these configurable electronics, such things like the charge trapping technology or the Wendorf's heterojunctions. But there are some limitations. Maybe in some of the technology, you need a very large consume a lot of power, or it takes a long time to realize the program. So in our case, we adopt the one very special structure, which is called the dual material gate structure. In this case, the gate electrode was constructed with two kind of metals. One is low work function metal, and another one is the high work function metal. And here showed the device structure, and the whole system was constructed on the a very thin paralleling substrate, so the system has a very good flexibility. And for the working mechanism, it is very simple. After we using two metal to construct the gate electrode. So these two metals have different work function. They will introduce this kind of modulation of the band structure in your channel. Here's my okay. You were so this step-like modulation of your band structure will be introduced in the channel, and when the device was worked in the transistor mode, in this case, the off-state current will be greatly suppressed, and so in the transistor mode, you will get a better on-off ratio, or we say that it get a better energy efficiency. Because this step-like modulation of the band structure in the channel, then in this case, the band structure in your channel is not symmetric anymore. So this device can also be worked as a diode. In this case, the gate electrode was just floated, and when you apply voltage between the source and the drain, in one way, you can get a large current, and in another way, the carrier will be blocked. So you will get this diode-like behavior. So, so we can see that just by changing the voltage you applied to the device, and also the where your voltage was applied, then you can just switch the device between our diode to our transistor. So you can just program where we say you can switch the device between two modes. And when we get the circuits to be more complicated, when we construct such kind of one device, one resistor circuits, then we can just switch the function of the circuits from between voltage follow to our rectifiers. And when we make the device more complicated, or make the circuits more complicated, when we involved two device, one resistor construction, then this integrated circuits can be just change its function from voltage adder to our OR gates. So it is configurable just depending on what's the function you want. For such kind of system, or we say the configurable ICs, it has a much flexibility. We say the function flexibility to just fit into different application requirements. Also, it has a better adaptability to the ever-change application circumstances. So it has this research field has attracted a lot of research interest. To summarize what I have talked today, and first of all, our research goal or our research interesting is such kind of flexible integrated smart sensor system. For such kind of system, in addition to the general characterized properties of the sensor, including the low power consumption, miniaturization, and when we want the system to interface with the biological surface, we need such a system to be flexible, and most importantly, it should be high performance, especially for the flexible ICs who take the responsibility to the information processing. And today I just show you several examples we have done for such kind of high performance flexible ICs, including we can construct the high performance CMOS ICs on the ultrathin substrate. Then we can construct such kind of ultrathin flexible system and integrate it with the sensor to work as a smart sensor system. And also we can construct the system by a transferable manner. In this system, we separate the fabrication and from the target substrate. So generally speaking, we can using this method to make the system to work with arbitrary substrates. And when we transfer the system onto a degradable substrate, and when we construct the whole system by using the degradable materials, then we can get such kind of degradable system, and it can be used for the eco-friendly sensor nodes to realize the environment monitoring. And at last, I show you some very interesting thing about the configurable system, and they can just changing their function when you just depend on your demand. And okay, finally, I would like to thank all my great group of members who make the work could be done here. I can show you here, and also my great collaborators at Peking University and at Hong Kong Polytech, and also Beijing University of Post and Telecommunications, and also funding source. And yeah, thank you for your listening, and I would like to take any questions.
Terrific. Thank you so much. Let me put up the the screen here. That was a wonderful talk. We have a number of questions from the audience for you. Let's see. The first one, what is or will be the cost of the carbon nanotube COMS IC?
So
do you have some sense of what maybe the best way to handle that is to compare what you expect in terms of fabrication? And actually a question that had come to me as well was, what do you see as the biggest bottleneck in terms of fabricating these kinds of devices?
Okay, I think there is the bottleneck of the CMOS IC maybe, so maybe the material. And currently for the flexible one, the dimension of the transistor is still very large, just around several micrometers. So in this case, we can using the carbon nanotube thin films. It works very well. But if we want to further decreasing, or we see the scaling down the dimension of the device, then we will have a higher requirement on the properties of the materials. Very recently, and there has been a very great demonstration on the rigid substrate that when you just align the carbon nanotubes to be just align the carbon nanotubes on the substrate with a certain degree of the density around the 100 per micrometers, then the performance or the speed of the device or the short circuits will be promote very, very high. So yeah, so if we can also gather such kind of materials on the flexible substrate, I think we can further scaling down the dimension of the device, and also, yeah, we can get an even higher speed on the flexible substrate or in the form of the flexible.
Very good. And our next question is, thank you, Professor Hu, for your wonderful talk. Carbon nanotube-based integrated circuits with ultra-low power consumption are really exciting. Do they have heat dissipation problems like conventional chips?
This is very great questions. And I have to say that for the one we achieved on the ultra-thin substrate, the first one for the CMOS one, and we find there is some problem of the heat dissipation problem with the heat dissipation. When we further increase the BIOS voltage, and we found there's we say that the current in the device cannot be promoted further. And we found that after the measurement of the device, we checking in the morphology of the device on the substrate, we find that there's some heating or the heating issues on the substrate. So if we want further promote the speed or the speed just depending on how much on-state current you can provide in your device. So if we further promote the on-state current, then there will be some issues related to the heat dissipation. And for the ultra low power, or maybe you refer to the second work we have done, that we transfer the device on the tissue surface. In this case, if we just want to get the ultra low power here, we just refer to the static power consumption. In this case, the requirement for the speed will be lower, or we say the requirement for the high on-state current will be lower. So the heat dissipation problems in this case will not so critical. Yeah. So there's just two different case.
Right. Yes, thank you. And then third question, many researchers in wearable sensors focus on sensor development and use commercialized printed circuit boards. How do you envision the combination of your carbon nanotube circuits with other people's efforts in this field? And can other researchers design and have their customized carbon nanotube circuits printed easily someday?
Also great, very great questions. And I think there's two approaches, and currently I think the great solution for the flexible integrated system maybe still depending on the printed circuit boards in these hybrid forms. But I think it will not be the ultimate solution. So that's why we are still trying to promote the performance of the flexible IC based on carbon nanotubes. So I think the both are very important. Just try to solve the problem from two different approaches. And if you are considering about the system just attached on the skin, so I think the printed circuit boards will be a good choice. But if you move the system from in vitro to in vivo to put in the body, then I think the fully flexible system will be a better choice. And if we can other researchers design and have their customized CNT device circuits, I think that's maybe the long goal, and just maybe one day we can design the CNT chips just as the things we have already done today on the silicon chips, right? So it's a long goal, but I think there's very promising. Yeah.
Wonderful. Well, thank you so much, not only for the beautiful work and talk, but also this discussion. We wanted to, normally in the world, we would walk across the stage and hand you a plaque and be able to shake your hand and congratulate you. But under these circumstances, at least, we wanted to recognize you as a rising star in nanoscience and nanotechnology for ACS Nano, and look forward both to your perspective article and your advice on the journal. It's beautiful to see your vision of the field, and we're looking forward to capturing that and your wisdom. So thank you so much.
Thank you. It's my great honor. Okay, thank you. Yeah.